Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques. In this video, we're going to take a look at sinusoidal functions and the vertical phase shift, up and down. So let's go ahead and get started. So if you look here, you can see that up in the corner we have a picture of a basic sine function. This is without any kind of manipulation of the period, the amplitude, the vertical or the horizontal phase shift or whatever. Nothing has been changed. And so just as a review, the basic equation that we often use for this is y equals a sine times the quantity of bx minus c plus d. And in this context, we know that a is the amplitude, amp for short. B is not the period, but b is what you use to determine the period. I've talked about that in the past. C, of course, is going to be the horizontal, back and forth like this phase shift. And now D, which is kind of the focus of today, so we'll kind of put a little, this is the up and down, the vertical phase shift. So that's what we're focusing on today. Now there's no special equation for the trying to figure out the value of D. You'll see in a second what I mean. It's just whatever the number is, that's what D is. So here's our first example. So the black line represents our regular sine function. You can see that it goes right through the zero here. Got the waves up and down. Nothing different here. However, this the orange line, it has a phase shift going up. In other words, the D value is going to be positive 1. So if I wrote the whole thing out, and I'm going to write out something that I don't necessarily need, but just to keep this clear, it's going to be 1 sine times the quantity of 1x minus 0 plus 1. So you can see our A is 1, our B is 1 here, our C is 0, and our D is 1. And so all these components right here are what you expect for a regular unmodified sine function. However, what is new is this plus 1 right here. And this is why it crosses the y-axis at 1. That's all that's happening there. So you can see there's no special equation for this. It's all a matter of looking at the value of D and knowing the answer. And so here, this time, if you look at the brown line, you can see that it's below the regular sine function. And so this is an example where the D value is negative 1. So again, if I wrote this out, it'd be 1 sine 1x. Again, I'm writing the ones just to complete the thought here. You don't need to do that. Minus 1. And so now the sine function, or the sinusoidal function in this particular situation, crosses the y-axis at negative 1 rather than 0. So again, there's nothing new, nothing fantastic there. All right, let's do this last one. Now this last one is kind of wild. This is kind of our wild card one for this particular video. And so you can see the purple function is is up there above it, and it's acting kind of weird, and there's all kind of interesting things going on here. So let's go ahead and take a look at this one. So the actual equation for this one is 2 sine times minus 2x plus 1 plus 2. All right, so let's just pull this apart piece by piece. So our A in this situation is going to be 2. That's this guy right here. Our B in this situation is going to be negative 2. That's this guy right here. Our C in this situation is going to be positive 1. That's this guy right here. And our D in this situation is going to be positive 2. You can see that. Now, let's take this piece by piece. Let's see if we can first figure out what the period is. So, gotta try to conserve some space here, but follow my thought. So the period is going to be 2 pi over the absolute value of B. So the absolute value of B is going to be 2, like so, which means that our period is going to be pi. And now, here's the thing. Because this is greater than 1, what's going to happen is that it's going to be compressed. And you can see that there are more, waves up here than there are compared to the regular sine function. It's compressed because in this situation, the B value here, the absolute value of B, it is greater than positive 1. So that's why it's compressed like that. There are more waves happening amongst the purple than amongst the black line, which is the regular sine function. All right, I skipped this, forgive me, but let's take a look at the amplitude now. So the amplitude is going to be, just change the color to make things clear. A is going to equal 1/2 times the absolute value of the maximum, which in this case the maximum is 4, and the minimum is 0. So, basically is 1/2 times 4, which basically you end up with an A that equals 2. Now, because this value of A is greater than 1, it's going to stretch. And so you can see here that the amplitude is 4 compared to 2. It's stretched. And when we talk about stretching and compressing, we're talking about in comparison to the regular sine function that has no manipulation to it. So the amplitude is stretched is 4, it's 2, when normally it's 1. Now you might be saying, but wait, the top value is 4 here. What do you mean? What do you mean that the value is 2? Well, normally remember that half the curve is above is positive, half the curve is below. But because of the D, which we haven't gotten to yet, it moved it up 2 units. That's why it's at 4 instead of at 2. So don't let that fool you. The amplitude is 2 compared to the regular sine function that has an amplitude of 1. That's what's happening there. So let's see here. We got that. Now again, some of this stuff is obvious because you can see right here, there's a 2 right here, it's obvious. But we're just going through the process because sometimes we don't have all this information and we have to calculate it. Now, let's talk about the shift to the left and to the right here, the horizontal shift. That is determined by C over B. So in this particular situation, the C is going to be 1. Let me change the color here so I don't lose anything. The C is going to be 1, and the B is going to be minus 2. That means we have a shift of basically minus 1/2, moving it a little bit to the, a little bit to the right, if you will. And you can see, I know this is kind of hard, but it's moved a little bit in terms of, it moved a little bit to the right. That's what happens when it's a negative, all right? So let's see here. So C, okay. All right, so the last one that we need to calculate is we're going to deal with now the, the D. There's nothing to calculate for the D. The D equals 2, positive 2, so we moved up 2 spaces, and that's pretty much it. So this is we're able to capture the behavior of this sinusoidal function by looking at the amplitude, the period, and the phase shift, both the vertical phase shift and the horizontal phase shift. So let me try to summarize what we talked about in this particular video and then wrap it up. So in this video, we talked about the phase shift, the vertical phase shift of a sinusoidal function. So we started by reviewing what a sine function is. This is the basic equation right here. And if you look at the chart here, you got a basic picture of the chart. And then I gave you an example of a vertical phase shift where it goes up 1. And so this all has to do with the D term, which is normally the last term if you write it in standard notation, if you will. Right here, there's no fancy formula. Just look for the number outside the parentheses, if you will. And then here's an example of when the D is minus 1. So we compare to the regular sine function, we're 1 unit lower in terms of where it crosses the y-axis. And then we did this crazy wild one that was quite different because we changed the various terms here by putting a 2 here, a negative 2 here, a 1 here, and a positive 2 here. And we calculated the period, the amplitude, we calculated the horizontal shift as well as the vertical shift. There's no calculating for that. And so we're just using a combination of these different terms here in the upper right hand corner. So I hope that this made sense and that you're able to get your mind around the behavior of sinusoidal functions and how they're similar to the regular sine function. So my name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.